Okay. So let me remind you where we were. No, before that, let me tell you where we're going. So we're going to understand multiplication today in the Heisenberg algebra. And also, hopefully, start dealing with composing operations. Because you see, at the end of the day, we want to compose many multiplications and many R things, R elements. So we want to know how to compose. And it will turn out that we need to understand Gaussians. And you probably have heard of Gaussians in many places. Well, here's another place where they occur. Okay? But first of all, let me remind you, so Rij, the R element, which we are yet to prove that it is an R element, but, well, we derived formulas for it. So the commutative formula for it is that it is the normal ordering of a commutative thing. And by the way, this commutative thing is a Gaussian. Namely, this is a coefficient, right? Because remember that e to the t is just a coefficient. So this is just a coefficient. And it multiplies something which is quadratic. So p variables multiplied by x variables, but still this is a quadratic. And that's exactly what a Gaussian is. A Gaussian is the exponential of a quadratic form. So here's our first Gaussian for today. We also defined the generating function map. Later it will be a morphism. You see, really it's a map from a space of homomorphisms to something. So, you know, soon it will become a morphism of categories. But anyway, we've defined these generating functions, and it's a map which maps homomorphisms of vector spaces between the vector spaces of polynomials in variables ZA into polynomials in variables ZB, where A and B are sets. So this is really a set of variables. So these are really polynomials in many variables. So we map such a homomorphism into its generating function, which is a power series in dual variables to the A's. Dual just means replace all Latin by Greek. And with coefficients that are the ZBs. And the definition of G was, so G maps L, so if L is a morphism from here to here, namely just a linear map, from here to here, then the generating function of L is, it's the exponential generating function of the values of A. So for each multi-index in the set of natural numbers to the power A, you look at zeta A to the power n. Again, that's just a monomial in the zetas, divided by n factorial, which is again a product of factorials, and multiplied by L applied to the corresponding monomial in the z's. Okay? And alternatively, this can be rewritten as L applied to the exponential of the duality thing. So the sum of over A of the zeta of each Greek variable corresponding multiplying the corresponding Latin one. We can call this calligraphic L sometimes to save writing the letter G. And this is completely mysterious. So calligraphic L is really a power series in the zetas and the z's. Well, power series in the zetas with coefficients that are polynomials in the z's. So it has both Greek letters and Latin letters in it. And I will always think of the Greek letters as coming on the left and the Latin letters as coming on the right even though mathematically it has no meaning whatsoever. But it will be useful later. Okay? So I want to give primarily two examples. Oh, so, sorry. The reason this is useful is precisely because of this O map. So O is a map, you know, I'll short it for O to O, but it's always O P before X. So O is a map from polynomials in PA and XA. So if you have a set of labels, you can look at variables P corresponding to these labels and X corresponding to these labels. So I suppose it's as if you're looking at Z's, twice as many Z's. So half the Z's are called X's and half the Z's are called P's. Okay? So O is a map from this to the Heisenberg algebra raised to the power A. So, and it's an isomorphism as of vector spaces. We're actually yet to prove this. This is the PBW theorem. We are yet to prove this, but I think I have a nice proof to show today, so I will. Okay? So, if we have a map between tensor powers of the Heisenberg algebra, it becomes a map between polynomial rings, and map between polynomial rings have generating functions. So all the things we want to do, maps between tensor powers of the Heisenberg algebra, become generating functions. So let me give you two examples. So example number one, what is the generating function of Rij? Wait, Rij is not a morphism between polynomial rings. Actually, it is. You see, Rij is a morphism between the polynomial ring in zero variables, namely the ground field. Namely, it's determined by its value on 1, so it's just an element. And the polynomial ring in Pi, Pj, sorry, what am I doing? Sorry. Rij is an element of the empty tensor power of H to the tensor power of H labeled by I and J. And when I write the generating function of this, I automatically think of it as if it's an element of the homomorphisms of the polynomial ring corresponding to the empty tensor power, namely the empty polynomial ring, into not the empty polynomial ring, the polynomial ring with zero variables. It's not empty, it has one element, it's called 1. No, it has infinitely many elements, it's one-dimensional. Sorry, anyway, it's this going into Q of Pi, Pj, Xi, Xj, right? And therefore, its generating function is a power series in 0 Greek letters and these Latin letters. And the power series is already written. It's this one. Okay? So the generating function of Rij is e to the t minus 1 times pi minus pj multiplying xj, I believe. Yes. Okay? So that's the first example. And the second example, we had other examples last time. I mean, these are examples for today. So here's the interesting example. So there is a multiplication map M going from, or let me call, yeah, sorry. There is a multiplication map M going from the Heisenberg algebra tensor Ij into the Heisenberg algebra tensor, it doesn't matter which notation I use, so one tensor factor, okay? And I want to find its generating function. So you know what, let me call this Heisenberg multiply, and let me call M the generating function. So M is, how do you write G? Wait, G. G of Hn. Okay? So how do I find M? Okay? So really, it's the generating function, so more precisely, or expanded, it's the generating function of a composition. First of all, I have to go from the the polynomial ring into, so really the thing written here should be a composition from polynomials in pi, pj, xi, xj into the Heisenberg algebra squared into the Heisenberg algebra just itself, and then backwards, so this is the map O, and this is the map O inverse, backwards into polynomials in one variable, in just one set of variables, so pk and xk. Right, it's the generating function of this composition. Okay? To compute this generating function, you just have to apply it to this exponential. Okay? So I have to take this exponential and push it through this composition. What is this exponential? This exponential is e to the, I have to take each of the variables here and multiply it by its Greek dual. Okay? So it will be pi I pi plus pi j pj plus, oh my god, psi I xi plus psi j xj. Right, so I have to take this polynomial, sorry, not this polynomial, this power series, and push it through, first of all, the ordering operator of all of these variables. So in some sense, it's the ordering up operator in tensor factor I, the ordering operator in tensor factor j. Yes?
Just a question about part one. The space where Rij lives, you said it's isomorphic to polynomials in zero variables.
No.
Or the map.
Rij lives in polynomials in in 4 variables.
Or the map from, is a map from polynomials in zero
Yeah.
variables to polynomials in 4.
Yeah.
This seems like a case where, like polynomials or power series in 0 variables with coefficients in polynomials in 4.
Yeah.
How is that power series in 4 variables?
Oh, it's not a power series in 4 variables. So you see, no, excellent question. We have an extra parameter here. The extra parameter is t. Okay, so really Rij belongs to this with t adjoined.
Okay.
So Rij is really a power series in the variable t whose coefficients are elements here.
Where is it?
Or as we wrote it before, this is in the Heisenberg algebra squared with t adjoined. So these are power series in t whose coefficients are elements of h squared. So if you expand this as a power series, so you see e to the t minus 1, sorry, no, this isn't the Heisenberg algebra, sorry, this is confusing. This isn't in the Heisenberg algebra. This thing is in the Heisenberg algebra with t adjoined. I mean, after I apply the G map, it's here.
Right.
Okay? Sorry. But anyway, so the original G, the original Rij, okay. In general, whenever you have an element of an algebra, e to the at is an element of that algebra with t adjoined. Right? You can think of it as a power series in the variable t whose coefficients are elements of the algebra. Powers are powers of A, but they're just elements of the algebra. So whenever you have the exponential of a parameter times something, you can think of it as a power series in that parameter with coefficients which are polynomials, just genuine or elements of the algebra.
Right.
Okay? So this is an element of H with T adjoined, and this is an element of, so really it's homomorphisms with T adjoined, and this, well, it's an element of that, but you can also, well, it's an element of the homomorphisms with T adjoined, but you can also view it as an element of Q, Pi, Pj, Xi, Xj with T adjoined. And you see, this thing, e to the t minus 1, starts with t. So if you, right, this is equal to t plus higher order terms. So if you expand this, you'll get higher and higher powers of t, but their coefficients will be elements of the algebra. So this is elements of polynomials in, sorry, not elements of the algebra, polynomials in P and X. So this is a power series in T with polynomial coefficients. Yes?
So you mean we have to map the O map on the Rij's before acting G on them, right?
Sorry?
So as you've written it, the Rij's belongs to the H with T adjoined. So we have to map the inverse map of the O inverse on the Rij's first before applying the G map.
In theory, you have to do exactly this.
Okay.
Okay, so, but the O map that you apply is the trivial one. The first O map that you apply is the trivial one because it applies to a space essentially empty. And the second O map is exactly the one we wrote here.
Nice.
Right? I mean, this can be written as Rij is, as this formula is O inverse of R. So if you do the second O inverse, you'll get that formula. I think maybe I skipped too much when showing example number 1. Yes?
Well, yeah, so about these T's, there isn't one T for each tensor factor.
No. No. T is one single variable, one single parameter for all.
But this is different from choosing our base ring instead of the rationals as the rationals adjoin T. Because
no, our base ring, it's the same as choosing the base ring to be the base ring to be the rational adjoint T, but then you have to complete with respect to T.
I see.
So you have to allow power series. Yeah, so, yeah, I don't know what to say. It's very delicate. Like, it's very delicate from the perspective of pure algebra. So probably the best way to think of it is not to think too hard from the perspective of pure algebra, but just think everything also depends on an additional parameter. So probably the best way to think about it, I mean, unless troubles arise, but sort of the best way to think of it is, just think of it as a bunch of formulas which depend on a parameter. Okay, and I don't explicitly write the space in which the dependence on the parameter happens. So think for every tiny t, this has a meaning. That's kind of the way an analyst would think of it, but okay. Anyway, I still have to compute this. I still have to complete this. So you have to feed this into O times O, then into Heisenberg multiply, and then into OK inverse. Okay? So that's a lengthy process. So first of all, let's feed it into O times O. Feeding it into O times O just means putting all the p's ahead of all the x's. Right? Now, also, this is still a commutative polynomial. Sorry, a commutative power series. Okay? So, so the exponential of a sum is the sum of the exponentials. Sorry, the product of the exponentials. So I can rewrite this as e to the pi I pi e to the psi I xi e to the pi j pj e to the psi j xj. Sorry, what I've written so far is just that. But now I need to apply OI tensor OJ. So the result is in the tensor factor, in the tensor product of two copies of the Heisenberg algebra. This is happening in HI, and this is in HJ. And in these two tensor factors, I put the p's ahead of the x's. So really this is pi I hat, xi hat, pi j hat, xj hat. Okay? Then, oh sorry, I'm not done. Now I need to apply the Heisenberg multiply and then the OK inverse. So the Heisenberg multiply just multiplies these two things. So I get e to the pi I. Well, pi is a coefficient, so it doesn't change. But pi, after I multiply in the Heisenberg algebra of I and j, in the two tensor factors, I write the result in tensor factor k. So this is pk hat after I apply multiplication. And then e to the psi I xk hat, e to the pi j, xk hat, no, p, sorry, what am I doing? pk hat, and e to the psi j xk hat, and to all of this I have to apply OK inverse. Okay, how do I apply, sorry, this is Blackboard. How do I apply OK inverse? I need to reorder this so that all the p's come before all the x's. Well, this p is good, this x is good, but these two are in the wrong order. Okay? So, I need a lemma. Lemma. In the Heisenberg algebra, e to the psi x, e to the pi p is equal to e to the minus psi pi e to the pi p e to the psi x. Yes?
I'm sorry, I confused about how you did the multiplication. So for the Heisenberg multiply, we need to multiply I and j's, right? But over here, I don't see where you are doing the I and j. So so the first E has a pi I and a pk, the index. I don't quite get it.
So pi is just a parameter.
Yes.
It stays. Okay. The element of the algebra is the p. So it's this, so I multiply this element with that element, with that element, with that element, and I put all of them in tensor factor number k. So that's exactly what I did. I replaced the p hats by p hat I with p hat k. That just means I put it in tensor factor k. This is an ordered product. This is a product in a non-commutative algebra. Okay? And the Greek variables here are all parameters, are the parameters of the generating functions. They're formal symbols, or if you're an analyst, they're small constants. Okay? They're tiny numbers. Okay? But still, I need to write this in the right order. Okay. If you've ever seen physics, you must have seen this relation before. This is the so-called Weil form of the a Heisenberg canonical commutation relations. So again, physicists use it all the time. We will prove it in a moment, but before proving it, I want to use it. Okay? So, by the Heisenberg, by the Weil form of the canonical commutation relation, I can swap exponentials of x with exponentials of p. Oh, sorry, this is all with hats. So, by the Weil form of the canonical commutation relations, I can swap them. And no, this is not hat. And the cost is a scalar. E to the minus psi pi is just a number, or a coefficient. So I can swap these two, and the price is a constant which I can pull out. So it's e to the minus psi I pi j times, okay, e to the pi I pk hat, e to the, now I flipped the order, so pi j pk hat, e to the psi I xk hat, e to the psi j xk hat, and I still need to apply OK inverse to this. Okay? But now, these two, oh, well, in fact, now all the p's are ahead of the x's. So the only thing OK inverse does is to drop the hats. So this is equal to, but once I drop the hats, all of these things are elements in a commutative algebra, and I'm just multiplying a bunch of polynomials. Sorry, of exponentials. So the result is the exponential of the sum. So this is e to the negative psi I pi j plus pi I plus pi j pk plus psi I plus psi j xk, and I have two things to say about it. First of all, where does it live? So this is a power series in the variables, the Greek variables. So the Greek variables are psi I, pi j, and pi j. So pi I, pi j, psi I, and psi j. And its coefficients are polynomials in pk and xk. So pk and xk. And that's exactly where it was supposed to live. That's exactly where a homomorphism from ij to k should live. Okay? So that was one comment. The second comment is that the thing here, well, this thing is again a Gaussian. Namely, it's the exponential of a quadratic, right? This is quadratic. All the terms here are quadratic. So this is the exponential of a quadratic. Notice that here the quadratic is a quadratic in Latin variables, Latin times Latin. And this quadratic has both terms which are Greek times Greek and Greek times Latin. So later when we will analyze quadratics, we will have to analyze quadratics that have all types of terms in it. Greek times Greek, Latin times Latin, Latin times Greek. You'll see that this generates interest. Call it complexity or interest, as you wish. Okay? Well, but we still have to prove the lemma. So this is super standard. You know, every quantum mechanics textbook will have it. So let me prove it, and there are a dozen proofs. I mean, I don't know, many proofs. Let me give you one. Okay? So I claim that the Heisenberg algebra acts on the ring of polynomials in one variable, the variable called x. Okay? In fact, it also acts on power series. Also, it acts on power series in x, and I think I will need to use both actions. They're the same. So I need to tell you how x hat acts, and how p hat acts. So x hat acts by x hat of a polynomial, so a function, is just x times this function. This is the multiplication operator by x. And p hat acting on f. So f is a function or a polynomial in the variable x, so p hat acts as differentiation with respect to x. So again, if you've seen quantum mechanics, this is super standard. So the position operator acts as, I don't know, have you seen quantum mechanics? So the position operator is a multiplication operator, and the momentum operator is a differentiation, and the relation they satisfy is the Heisenberg commutation relation. I have to check that. So I have to check that indeed this is an action, namely that p hat, I need to check that p hat commutator with x hat is equal to the identity. So I need to check that the commutator of differentiation and multiplication by x is 1, is do nothing. So let's check this. So, so in other words, I need to check that dx x minus x dx is equal to the identity. Okay? So let's see. Let's apply it to some function f. So dx x hat f minus x hat dx f, is it equal to f? Well, this is Leibniz's rule. So by Leibniz's rule, dx acting on x times f is well, dx either acts on x, so then you get f, or it acts on the f, and then you get x dx f minus x dx f. These two cancels, and we check. Okay? So h indeed acts on polynomials. This, by the way, proves PBW aside. This means, it implies, this proves PBW. Namely, so if you have some xi, or some aij, x to the I, dx to the j, so this is, so we need to, okay, sorry, let me be more precise. In the Heisenberg algebra, we need to show that some aij xi hat pj hat is not zero, right? Because we need to show that the ordering map, actually I took the reverse ordering here. I've put the p's on the right, and so, but it's the same. I mean, after all, there is the algebra has some automorphism that flips p and x. It's really not. So I need to show that this is non-zero in the Heisenberg algebra, right? We needed to show that the ordering map it was clearly onto. We needed to show that it's injective, so we need to show that this is non-zero in the Heisenberg algebra. Well, all we need to show is that it acts non-trivially on Q of x. On Q of x, it acts like the differential operator sum aij xi d to dx, x to the I, d to dx to the j. And it's easy to show that this differential operator acts non-trivially on polynomials. For example, what's the loveliest polynomial you can act on? Well, the loveliest polynomial you can act on is, so let's see how this acts on the polynomial e to the tx. Well, that's not a polynomial, right? But it's a polynomial if t is it's a function, or you can view it as a polynomial where I've allowed a power series parameter. Okay? So really, I can extend this representation to a representation which allows another parameter. Okay? And then how does it act on it? So this operator, let's call it D, and let's call this function G, then dg is equal to, so if you differentiate with respect to x, j times, every time you differentiate with respect to x, it pulls down a power of t. And then every time you multiply by x to the I, it multiplies by x. So this is sum of aij x to the I, t to the j, times the original g, times g. And since this is a non-trivial polynomial, this must have been a non-trivial polynomial to start with. Okay. But we're not done with proving the Weyl commutation relation. So let's prove it. So in fact, since I know that, as I know that any non-zero D acts non-trivially on G, it's enough that I check that the two sides of the Weyl commutation relation acts in the same way on G. Right? So it's enough that I check that e to the psi x e to the pi p minus e to the minus psi. Oh, what have I done? sorry, minus psi pi e to the pi p e to the psi x, it's enough that I check that this is equal to 0. By the way, where is this happening? This is happening in Q polynomials in X into which I've allowed coefficients which are power series in psi, pi, and t. In fact, t is unnecessary. I could have, t is unnecessary here. You could have done without it, but you could, but still I could write it this way. So all I have to do is to check in general, okay? So let's check in general how does each of these things act on G. Okay? So e to the psi x hat acting on G is, so x hat is just multiplication by x hat, by x. So e to the psi x hat will be just multiplication by psi x, sorry, by e to the psi x. So this is just e to the psi x times G. The more interesting one is e to the pi p hat. How does this act on G? So by definition, this is e to the pi differentiation with respect to x acting on G. You know, let me change my mind. This is not even true for this G. This is true for every function f. I don't need to know that it's our function G. It's also true for our G, but it's more general. So do people know how does the exponential of the derivative act on a function? Do you? Yeah?
Isn't it evaluation?
It's sort of evaluation. It's a shift operator. Oh my God. Okay, can I go 5 minutes over? Okay, this is like one of the sort of most brillianter things in mathematics. Brilliant test. One of the things that, well, makes life worth living. I don't know, sorry. So,
Is it kind
in
of
general, what is e to the, well, you know, I may as well keep the variables. What is this acting on a function f, where f is a function of the variable x? So in other words, so f is a function of the variable x. I need to evaluate this. I mean, if the result is again a function. So let's compute it at the point x. Okay? What is the result? The result is sum pi to the n divided by, multiplied by d to dx dn, dx to the n divided by n factorial, applied to the function f of x. Okay? But this is Taylor's formula.
oh,
So this is f of x plus pi. So this is a shift operator. Okay? So if f is a polynomial, this is again a polynomial, all right? But this is just Taylor's formula. Right? This is by Taylor. Right? You're differentiating f n times, you get n times. I mean, you know, let me write an intermediate step. This is sum pi n divided by n factorial, the nth derivative of f at x. That's exactly the Taylor's formula for that. So this is just f of x plus pi. But now I can apply this to our g. Okay? So applying e to the pi p to g gives us g to the g at pi plus x multiplied by e to the psi x, and we want to ask ourselves, is this equal to e to the minus psi pi e to the and then you take the function e to the psi x multiplied by g and shift it by p, by pi. So to which do you apply the transformation? X goes to x plus pi. So now so this is e to the left hand side stays. So let me just simplify the right hand side. So this is e to the negative psi pi e to the psi x plus pi g at pi plus x. This cancels that, and you're done. Sorry, so I lied to you. I didn't need to use our specific g. I could have used any g. It didn't matter. Okay, we're done. Sorry for going 3 minutes
Oh, no,
over
that's all
time.
right.